more complicated because you need to choose 4 parameters and not 2. And so the question is, or are you choosing these 4 parameters instead of the 2 of before? And this is what we will discuss. Or are we choosing this one, this one, this one, and this one? Okay? And what will we do in order to understand how will we choose these design parameters? I will go back to my fundamentals. I'm going back to my fundamentals. And my fundamental was I need to reduce Vjet. Vjet is coming from where? Vjet is coming from the energy that you have at the exit of the turbine. Okay? This is coming from there. And the energy that you have at the exit of the turbine, this is related with the power delivered by the turbine. If you are able to increase this one, you will reach a lower energy behind the turbine, so a lower Vjet. And the PIT, it's equal to what? In this case, this is equal to the PI of the low pressure compressor plus the PI of the high pressure compressor. This multiplied by beta because there are also accessories and, let's say, some friction losses in bearings and other things. I'm interested just by the evolution. So let's say that this is equal to 1. Okay? What is passing inside the turbine? This is m dot p plus m dot f. This is the mass flow rate in the turbine. Multiplied by Cp average of the gases, multiplied by Tt3 minus Tt4. And this is equal to what is passing in the low pressure compressor. This is m dot secondary plus m dot primary. Both are passing in the low pressure compressor. Cp of air average. And we have there Tt1.5 minus Tt1. And what is passing in the high pressure compressor? Only the m dot p. You have Cp of air, but not the same, because we don't have the same temperatures. And you have here Tt2 minus Tt1.5. Okay? Let's say the Cp are the same. I know they are not the same, but I'm only interested by evolutions, by some trends. So I cancel this. I also say m dot f is small compared to what I have in m dot p and in m dot secondary. And I divide everything by m dot p. So here I have 1, here I have 1, here I have 1, and here I have the bypass ratio. And I put here Tt3 in evidence. So I have 1 minus Tt4 divided by Tt3 is equal to what? You see that I have the bypass ratio here, the bypass ratio, multiplied by Tt1.5 minus Tt1, and I put Tt1 here. And so I have Tt1.5 divided by Tt1 minus 1. And here I have, you see, 1 Tt1.5 minus Tt1, 1 Tt2 minus Tt1.5. I have Tt2 minus Tt1. I write this Tt1 and here Tt2 divided by Tt1 minus 1. Okay? I divide everything by Tt1. Why do I say that? Because I like this parameter that is coming back from my basic gas turbine cycle. This is disappearing. And what do I have here? I will write it in this way, because this is, let's say, a nice formulation. I have Tt3 divided by Tt1. This is my parameter I like since the beginning. I have 1 minus what? It is here related with Pt4 divided by Pt3 to a power that is function of gamma. And this is equal to the second term. I write it like this. Bpr multiplied by the PLPC to a function of gamma minus 1 plus the P global, this is what is called very often P global, because PC, there are two compressors, so it's better to say P global. Again, function of gamma minus 1. And so, what have I written? And after that, we do a short break, because I'm sure you are interested to drink coffee after this theory. What do we have? Look at this equation. Look at this equation. What have I said? We need to have the 4 design parameters. I have recalled PC P global. Where is P global? It's here. Where is the TIT? It's here. And even under the form I like, Tt3 divided by Tt1. Where is PLPC? It's here. And where is my force parameter? It's here. So I have 1, 2, 3, 4 design parameters. The rest is what? 1, 1, 1, and I have this. And this is what? This is VJet. Because PT4 will influence VJet, so here somewhere you have VJet. Which VJet? And then I'm concluding the VJet here. And this VJet is what I call VJet P. Because maybe you have already observed that we have not only introduced 2 different mass flow rates, we have also introduced 2 different ejection speeds. We have also an ejection speed for the secondary flow. And here, the speed that we have, this is the primary. The primary. And so we see that we have obtained an equation that is linking the primary ejection speed, the ejection speed of the primary flow, with 1, 2, 3, 4 design parameters. And you see that VJet P must be small. So PT4 must be small, so this must be high. And how can you have this high? You can have this high by having this high, by having this high, and by having this high. We see that in order to decrease VJet P, we must increase the bypass ratio. We had already this feeling a few minutes ago. We have to increase the pressure ratio of the low pressure compressor, and we need to increase the global pressure ratio of the full compressor. I will come back on that in a few minutes after your coffee cup.